We also looked at finding angle measurements in a polygon. How do you find the sum of the angle measurements in a polygon, in a convex polygon? Nicole. Very good. The number of sides minus 2 times 180 degrees. Yesterday we left off with example 3. Here we have find the value of x in the diagram shown below. What type of shape do we have here? Kara? Try again. One more chance. It's a pentagon minus 1. Minus 1. Very good. It's quadrilateral. Yes. It is a quadrilateral. What do we know about the interior angles of a quadrilateral? Tyler? Add up to equal 360. Very good. So we have 135 plus 71 plus 112 plus x equals 360. 135 plus 71 plus 112. What is that? 135 plus 71 plus 112. Nicole? 318 plus x equals 360. Subtract 318 from both sides. So what does x equal? 42. Very good. X equals 42. Theorem 8.2. Exterior angle theorem. This says the sum of the measures of the exterior angles of a convex polygon, one at each vertex, is 360 degrees. The sum of the measures of the exterior angles of a convex polygon, one at each vertex, is 360 degrees. So once again, we're talking about the sum of the measures of the exterior angles. What is an exterior angle? What is an exterior angle? How do you know when you have one? Andy? Okay, it is on the outside, but we need a little bit more than that. It's not just on the outside. What else? How do you know when it's an exterior angle? This takes us back to chapter 4. Kellen, what's an exterior angle? Okay, it's adjacent to the interior. Good. What is it with the interior? It's a what with the interior? Killian. It's a linear pair with the interior. Very good. So, if I were to call this angle here, angle 6, it is angle 1 is an exterior angle with angle 6. But angle 6 has two exterior angles. I could draw this line here going this way, call this 7, and now it's an exterior angle here. Okay, so when we say one at each vertex, that's because every interior angle has two exterior angles. But with this theorem, we only want to count one at each vertex. Therefore, essentially, the interior angles of a polygon will equal the exterior angles of a polygon with this theorem, in terms of this theorem. So, according to this theorem, when I add up all the exterior angles, one at each vertex, it's going to equal 360 degrees all the time for every type of polygon. Whether it's a nonagon, a dodecagon, a pentagon, it doesn't matter. All of the exterior angles added together, one at each vertex, will be 360. So we could do 1 plus 2 plus 3 plus 4 plus 5. It's going to equal 360. We could do 7 plus 2 plus 3 plus 4 plus 5, and that will equal 360. What you cannot do is 1 plus 7 plus 2 plus 3 plus 4 plus 5. 1 at each vertex will equal 360. Right now, I want you to try example 4 on your own, please. Christina, how do we do it? Very good. Combine like terms, 2x and x, that's 3x. 89 plus 85, 174. Equals 360. Subtract 174 from each side. What's 360 minus 174? What? 186. 3x equals 186. So x equals 62. Example 5. The base of a lamp is in the shape of a regular 15-gon. Find the measure of each interior angle and the measure of each exterior angle. A regular 15-gon. What's that mean to be regular? Lauren. Sorry, equiangular and... Yes, it's equiangular and equilateral. All of the sides are congruent. All of the angles are congruent. So, we want to find the measure of each interior angle and the measure of each exterior angle. Pierce, how are we going to do it? So we would do 15 minus 2 times 180. And that's 13 times 180, which is what? 2,340. Good. That 2,340 degrees, Daniela, what's it represent? The sum of all the angles added together. So now how do I get the measure of one of the interior angles? Keegan. Divided by 15. Very good. Because there's 15 angles in it. So what is 2340 divided by 15? Danny. 156? 156 degrees. So the interior angle is 156. How do we find the exterior? Max. Okay, we can do 15x equals 360. Remember, there are 15 exterior angles, so we divide each side by 15. So what does x equal, Max? 24, very good. How else could you have found the exterior angle? Sarah? Yeah, you could do 180 minus 156 because they're a linear pair. Now, that's one way you could have done this, where you start with the interior angle, and you find that, and then you find the exterior. What's another way you could have done it? Max actually wasn't that far off. Max, what could you have done first? You can start with the exterior. There's going to be 15 exterior angles. You know when you add them all together, they have to equal 360. Divide by 15, x equals 24. So you get 24 degrees for the exterior. Now, how can you get the interior? Pierce. 180 minus 24 will give you the interior at 156. So you can do it on the left or on the right, it doesn't matter. Yeah. I'm sorry, what? Why does it work? Oh, subtract 20, because an exterior angle is what with an interior? Linear pair, which means it's supplementary. So that's why we can do 180 minus 24. Okay? Questions on that? Questions on that? Okay, going into section 8.2. This section, we already pretty much did most of it because this is how we reviewed and practiced for the coordinate proofs in chapter 5. But we'll run back through it and retouch upon these things. That way we're all on the same page. So it starts off with a parallelogram. What's a parallelogram? What's a parallelogram, Tyler? Very good. Quadrilateral with both pairs of opposite sides parallel. Now, what's the first thing that we proved about a parallelogram? We did a coordinate proof, and we proved what about a parallelogram, Pierce? Very good. We proved the opposite sides to be congruent. So QR is congruent to PS, and QP is congruent to RS. Now, then I gave you a theorem about parallelograms. What theorem did I give you about a parallelogram? Edmund. Good. The opposite angles of a parallelogram are congruent. So Q is congruent to S. P is congruent to R. And then we did another proof. What did we prove about a parallelogram then? What? Keep turning the page. Ah, there it is, yes. What did we prove about the parallelogram? Andy? No, not the diagonals are congruent. We proved that the diagonals have a what? Have the same midpoint. If the diagonals have the same midpoint, then what do they do to each other? Keegan? They bisect each other. Very good. So we proved that the diagonals bisect each other. So PR bisects QS, and QS bisects PR. And that was this theorem here. It says if a quadrilateral is a parallelogram, then its diagonals bisect each other. Okay, I want to skip back 2 pages in your notes. I want to go to this proof here, please. Okay, now, we're going to change it a little bit up here. In your notes, it says that Q plus P equals 180, and R plus S equals 180. We want to make Q and P supplementary, and I want to make angle P and angle S supplementary. So we're not going to prove they equal 180, we're going to prove they're supplementary. So we'll start off with PQRS as a parallelogram. That's my symbol for parallelogram. Okay, so we know it's a parallelogram. Tell me, what do we know about a parallelogram that will help us get Q and P to be supplementary and P and S to be supplementary? Kara. QP is congruent to RS. Justification. Very good. Parallelogram, opposite sides. Now, with the opposite sides being congruent, will that help us get the angles to be supplementary? No. So you could put that in there, but it's not wrong, but we don't need it, so I'm not going to put it in there. I'm going to make this a little bit more precise for us. Maureen. Justification. Yes, they are congruent. How is that going to help me get Q and P to be supplementary? I don't know. Okay. You guys are overlooking the most obvious thing here that will help. Pierce. Why is QR parallel to PS? Definition of a parallelogram. Now, if these two sides are parallel, what do we know then? Danny. Very good. If you look here, Q and P form that letter C, right? So there you have your co-interior angles. So, when these lines are parallel, Q and P will be supplementary. So, we'll make QR parallel to PS. And what else, while we're in this same step, what else can we do? Amber? Yep. And that's definition of a parallelogram. Okay, next step, with those two sides being parallel. Danny. Okay. Claire, justification. I'm sorry, what? Co-interior angles. Thank you.
Claire, where's your name? Claire. Oh. Claire. I thought he was just screaming that.
Claire, what is the justification? Good. Co-interior angle supplementary. Okay, Q and P are supplementary. What else do we know? Colleen. Good. P and S are supplementary. And that's going to be the same justification. What else do we know? Tell me everything else we know. Because these lines are parallel, what else do we know? We know Q and P are supplementary, P and S are supplementary. What else is going to... Molly. Q and R are supplementary. Very good. And what else is going to be supplementary? Pierce? P and S we already proved. We have QP, QR, PS, and what's the last pair, Tyler? RS. Very good. So all of the consecutive angles are going to be supplementary. If a quadrilateral is a parallelogram, then its consecutive angles are supplementary. What's the title of this section, Christina? Properties of parallelograms. Section title is a little bit misleading. What other shapes are parallelograms? Kellen. Squares, good. What else? Yeah. Rectangles, good. What else? Nathan. Rhombus, very good. So this isn't just properties of parallelograms, this is also properties of what? What else are these properties of? Yeah. And, very good. So when we say properties of parallelograms, keep in mind, properties of parallelograms include the rectangle, the rhombus, and the square. So all of these properties that we just proved, that we have theorems for, they apply to these shapes because they are parallelograms. So in a rhombus, the opposite sides are parallel. Why? Definition of a parallelogram, because a rhombus is a parallelogram. You cannot have a rhombus that is not a parallelogram. Every single rhombus will always be a parallelogram. Yes? No, not necessarily. No, I wouldn't mark that wrong. No, no. Okay, your assignment for this evening. 8.1b. 8.1b. Numbers 16 through 35. 8.1b, 16 through 35.